Okay, so welcome everybody for this second day and last day in this workshop and to this early morning session. Welcome to our early morning speaker Stefano Borghini from Milano Bicocca, who will talk about the characterization of static spacetimes. Yes.
Thank you for the introduction, and yeah, you can hear me, yes, I guess. Thank you for the introduction, and thank you for inviting me here. So it's always nice to come back to Pisa, and it's always nice to be in presence again. I was growing a bit tired of talking to myself in my office in front of a screen. So it's nice. This is much nicer. So today I want to talk about static spacetimes in general relativity. Before talking about them, I'll try to give a sort of overview of some of the topics that are interesting in mathematical general relativity. So this will take possibly half of the talk, and I mean, with the purpose is to give some overview of what the topic is about, and also to kind of act as motivation for our work and how it sits in the literature. So let me start with from the basics. So what is a space-time? So space-time would be for us a four-dimensional manifold. So four-dimensional manifold endowed with a four-dimensional metric, which is Lorentzian. So it is not Riemannian. It has signature. It's a pseudo-Riemannian metric. So it's signature 3-1. The positive directions, the three positive directions correspond to the space in some sense, and the negative direction should be thought as the time direction. Okay, and we want this four-dimensional manifold to satisfy. So it's a Lorentzian manifold satisfying the Einstein field equations, which are these ones. So, I always forget. 1/2. So equal to t. So here I'm denoting by Ricci gamma and R gamma the Ricci curvature and scalar curvature of the metric gamma. Lambda is the so-called cosmological constant. And T is the so-called stress energy tensor. So lambda is just a number, just a real number. The stress energy tensor is a symmetric 2 tensor that in some sense encloses what is known about the mass and energy in our space-time. Okay, so this is well, Einstein field equations, and then let's see. So this is the framework from where we start whenever we want to study anything in mathematical general relativity. But now, so this is a space-time, so space and time are in some sense interconnected, and so there's no real way to talk about an instant in time. So two events happen. It's not really meaningful to say that they are happening at the same time or something like that. So there's not real notion of instant in time. The closest to this notion is what is called initial data set. Initial data formulation of GR. So what is that? So what you can imagine as an instant in time is a three-dimensional manifold. So this is our space. This is our space-time. Inside we take a three-dimensional manifold. G is the metric induced by gamma on this manifold. And we want this metric G to be Riemannian. In some sense, we are asking that the time direction, so the negative, the one where the signature is negative, is transversal to this space-time. Okay. So when one restricts, when one write down the Quadratic equation, Gauss Quadratic equation, starting from this one, restricting them to the manifold Mg, one finds these equations here, which I'm writing for completeness. Two lambda plus 16 pi rho. We will not use them that much, but let me write them down just once and never again. Theta k equal to mu. So the scalar curvature of the metric. So from this one, we get these equations here, which are the Einstein constraint equations. So where here k is the second fundamental form of this manifold Mg. This is the scalar curvature. This is the trace of the second fundamental form. So that's the mean curvature. And these rho and mu that appear on the other side, these are components coming from the stress energy tensor. Okay, and it is physically reasonable to expect that this rho is greater or equal than 0. In some sense, in some imprecise sense, it is sort of the energy density of the space, but it's in a very imprecise sense. But you expect it to be negative. And so now we will not discuss the full equations in general. So this is kind of the way how one starts from something Lorentzian and ends up with something completely Riemannian. Okay. The important thing, the crucial thing from the point of view, from the physical point of view, is that this is, I mean, some sort of converse is also true. So once you are given a tripole like this, MGK, satisfying the Einstein constraint equation. So if you are given just this, a three-dimensional manifold, symmetric to tensor satisfying these equations here, then for a lot of matter fields, there's a unique way to extend this one to a full space-time. So in some sense, this is what makes general relativity physically viable as a theory. I mean, you can, if you know everything about an instant in time, then you can find predictions. I mean, reconstruct the whole space-time starting from that one. Okay, so in some sense, it is enough, in some sense, to discuss what happens on a singular slice of the space-time. Okay, and now we will focus actually on something very much less ambitious. So let me assume first that k is equal to 0. So this is the so-called time symmetric case. And you can imagine why. Is it called time symmetric? I mean, if k is equal to 0, I'm having some trouble with this. If k is equal to 0, then the only, so there is a unique way to extend it as a full space-time. And since k is equal to 0, you can flip it. I mean, there's a clear reflection in the way you can extend the space-time. And so that's where the name comes from. And if you plug in k equal to 0 inside these equations, things simplify significantly. You are just left with scalar curvature equal to 2 lambda plus 16 pi rho. And since it's reasonable to assume that rho is greater or equal than 0, what we get actually is just scalar curvature greater or equal than 2 lambda. So what we are actually interested in studying are just three-dimensional Riemannian manifolds satisfying this bound on the scalar curvature. Okay. So what does one want to study about these manifolds? One wants I mean, one would want to find physically reasonable statements that are interesting in this framework here. And I will cite a couple. Let me focus now on the case that is most known in the literature and the one in which we are able to say the most, which is the case where the cosmological constant lambda is equal to 0. So now I will focus for a moment on the case of 0 cosmological constant. Let me write it down, maybe some part of the blackboard. So when lambda is equal to 0, we actually have a lot of information I mean, there are some powerful theorems concerning manifolds with this bound. So now, our framework is a three-dimensional Riemannian manifold with scalar curvature greater or equal than 0. Okay, and so one of the usual assumption that one makes, because one needs some more assumption in order to find something meaningful here, is the so-called is to ask for the manifold to be asymptotically flat. What is an asymptotically flat manifold? It is a manifold that I will draw a picture and I'll try to. So you expect, so it's a manifold shaped like this. So there's some compact part of the manifold where everything can happen, but you want that asymptotically, the metric here looks like the metric on the standard tree space, plus some error term that behaves nicely enough. So it goes to 0 fast enough. And that's not really the point of the talk to say what's the sharpest way epsilon should go to 0. What is important instead is that for such manifolds, which are physically reasonable in the sense that essentially what they model is isolated systems. So if you get a galaxy or a star or something like that, you can expect that. So here you can have whatever you want, a galaxy, a star, whatever. And then at large distances, then the gravity effect of that isolated system shouldn't matter that much. And so you should be almost R3. Okay. So this is more or less the heuristic behind this definition and why it is interesting from a physical perspective. And what's interesting also to a mathematical perspective is that one can define a total mass for this sort of spaces, which is defined as such. So I should have put a limit somewhere. So it is the integral over large spheres of radius r, where r is large. So at infinity, it makes sense to talk about spheres because we are essentially in R3. Of what? Of the alpha g alpha beta minus d beta g alpha alpha in beta. Well, the actual expression, again, is not really important. What's important is that, in some sense, it measures, the mass measures, in some sense, how fast the metric is decaying to the Euclidean metric at infinity. So that's essentially what's important about this definition. And notice that this definition is very chart dependent. I mean, here it's all written in coordinates. Okay, so it's actually important that, I mean, it's been proven by Bartnik and Krushel as well, that this mass actually does not depend on the chart at infinity. So it doesn't depend what kind of chart you're taking at infinity. The result you get is the same. So the ADM mass is a well-defined invariant for the three-dimensional manifold. And it has a couple of properties that are very desirable. So the first one is the so-called positive mass theorem, which I guess some people are familiar with already. So in this framework, so MG, so at a manifold MG with scalar curvature greater or equal than 0, and with boundary, with empty boundary, then the ADM mass is greater or equal than 0 by force, which is something that is expected from a mass. And the second property is that if the ADM mass is equal to 0, then URR3, so MG is just isometric to the Euclidean space with the standard metric. Okay, so we have a very powerful rigidity statement in this case. And I don't know where to write the other one. I didn't want to invade on the other side. Well, let me mention that there's another result, which is in, well, no, let me invade on the other side. There's no way I can make it here. So, Riemannian inequality. So this instead deals with the case where the boundary is non-empty, and we want it to be a compact outermost minimal surface. So what such a boundary should represent should represent an horizon for some black hole that is hidden behind this horizon, so we are not seeing it. But what we expect is that such boundaries should contribute to the mass because they are enclosing some black hole inside. So we expect that the mass is not actually zero, it is strictly positive, and this is the content of this result, I mean, of the Riemannian Peres inequality, which states that the mass is greater or equal than what? I always forget this term. The mass is greater or equal than square root of the area of the boundary divided by 16 pi. Okay. So this is the result, and again we have a rigidity statement. So if the ADM mass is equal to this threshold here, then this time we are the Schwarzschild solution. What is the Schwarzschild? I guess some of you have already seen it, but is the simplest model of a black hole. So it is this structure here. So the manifold is R3 minus a ball of radius 2m, and the metric has this form with respect to radial coordinates, r squared divided by 1 minus 2m over r plus r squared gs2. So it is defined on R3 minus a ball. This is the horizon that one gets, and you expect the black hole to be inside here. And m, and this parameter m that appears in the formula is actually the ADM mass of the Schwarzschild solution. So this is the simplest model of a black hole that we have, okay? And in fact, is the one that realizes the infimum in this inequality here. Okay. Yes. Oh yeah, that's actually true. Yeah, there's no minimal surfaces. I mean, there's no other minimal surfaces inside. So so what can happen in principle, if you don't ask for it, is that, I mean, you have your manifold done whatever way you want, and then you can have some sort of bottleneck, and then it grows again, and then it becomes bigger. Okay, and so you shouldn't really compare with this minimal surface here. You should compare with the first one. So you should compare with the smaller one that you found. Okay, so it's not really fair to hide a higher boundary inside a minimal surface coming before it. Okay, so outermost means that there's no such thing as this. There's no minimal surface here. Thanks. Yeah, I should have I should have mentioned what that means. Yeah, because yes, it's not really familiar to everybody. Yeah, so this is more or less the. So this is not allowed. Otherwise, you can get whatever. I mean, you can get as close to zero as you want. Okay. Okay, and so staying in the. What time is it? Should I put it? What time is it? 9:15. Good. I know that I have all the time, but I don't even want to stay 2 hours here. Great. I'm sure you will be delighted to hear me talk for 24 hours. Okay, so let me finally talk a little bit about static spacetimes. So first in general, and then what we can say for lambda equal to 0 again. So this one. So let's finally get into static. So this time we are asking much more. So before we were asking that we had these 3 manifold inside our spacetimes, and we were not asking too much about this manifold. Well, we were asking k equal to 0, but that's a very strong hypothesis, but it's actually not as strong as it sounds in the sense that that case encloses many of the difficulties for many of the problems in that case. But here we are assuming much more. We're assuming that we have our 3 manifold Mg, and that the entire space-time splits with respect to this manifold. So the 4 manifold is now just isometric R times 3 manifold M. And we are assuming vacuum, so T will be equal to 0 now. And finally, the metric also splits as minus U squared dt squared plus a metric G, which is a metric on M. So Mg is again a 3-dimensional Riemannian manifold. I guess you can believe me, this is much more than before. Of course, here k is equal to 0. It's much more. Everything splits. It's the nicest possible case. And in this, with respect to this hypothesis here, then if you start from the Einstein field equations that I erased before, you get a system of equations that looks as follows. Here, Ricci equal to the Hessian. So the Ricci tensor is connected to the Hessian of the function u plus lambda ug in case we have a cosmological constant. The Laplacian of u is minus lambda u in case you have a cosmological constant. And in case you have boundaries, it makes sense to make them coincide with the 0 level set of u. So we have u equal to 0 on the boundary, and it makes sense to us that u is positive in the interior of N. Okay, so this is the problem that one studies when one wants to study vacuum static spacetimes. So now things are much simpler. So we are left with the study of a PD problem on a Riemannian manifold. Okay, and it's not something crazy. It's something that in some ways one has seen, I guess, some connection between the Ricci tensor and the Hessian, and U, it must be an eigenvalue of the Laplacian. Okay, and what we expect here is much more. So we don't just expect that we can say something on the physics of the system. Here we expect that we should be able to classify static spacetime. So the ultimate goal is to classify vacuum static spacetime. They are, in some sense, the easiest, in some sense, in many senses, they are the easiest solutions to the Einstein field equations, and they are kind of the building blocks where you can perturb and find something more real. So you should expect that this should be, in some sense, easy to classify, or at least it should be doable to find what are the possible static solutions, the possible easier solution to the Einstein field equations. In fact, this is not trivial at all. So let me discuss briefly the case lambda equal to 0, because this is actually quite well understood. So here there's a quite famous theorem, which is the so-called black hole uniqueness theorem. The black hole uniqueness theorem states that when lambda equal to 0, if you are a static vacuum solution, I mean, there are the only possibilities. Okay. If you ask asymptotically flat, there are essentially two possibilities. So two possibilities. I mean, it is either the flat spacetime, so it's either just R3 with the standard metric, or it is the Schwarzschild. Well, the one that I brought. The one that I wrote before. So these are the only models of static spacetime, provided we are asking asymptotically flat. But this is already quite a strong result. And it just occurred to me that I might mention as well, at least about these theorems, who are they do for? I mean, who proved them first? I guess it's only fair because they are pretty big theorems and they are pretty big names. So concerning positive mass theorem, it was proven by Shen Yao. And later, well, almost at the same time by Witten with a completely different method. And then there are many other proofs, even in the non-time symmetric case. So there's a lot of literature here, starting from these two papers, essentially, three papers. Concerning the Riemannian Paris inequality, it was first made in an article that has been, I think, already mentioned, Hiesmayr and later by Bray. So Hiesmayr did the case where the boundary is connected, and then Bray extended it to non-connected boundaries. Different, okay, they are geometric flows. So Hiesmayr used the inverse curvature flow. No, Bray uses a conformal flow that I don't remember, but it's something more specific. But essentially, it takes into account multiple components better than inverse curvature flow. I don't remember. And finally, black hole uniqueness theorem has been proven in different generalities by a lot of people. But I guess I mean, there's a paper by Israel, and then second one, Robin, and there's a paper by Robinson, and then finally, in one thing, Masoud Alam is the paper that most people cite. And what's remarkable about this paper is that they prove this result passing through the positive mass theorem, which is something that belongs to a completely different framework, but they are able to start from their static solution and make the mass appear in a way that they can trigger the rigidity statement of the positive mass theorem. It's a neat trick that I will not discuss, but just says something about the fact that positive mass theorems in general sometimes can give strong information on static solutions as well. And this is not the only example. So this is essentially what's known. And I should mention recent papers by Reiris as well. So there's some recent papers by Reiris which deal with the not asymptotically flat case. So he's almost able to remove that hypothesis completely. At the cost that these are not the only possibilities anymore. So there's a couple more examples if you don't assume asymptotically flat, but this should be it. We should have a complete picture. The proof is not complete yet. I mean, there's some hypotheses that I has to make, but they are not. I mean, the conclusion is not as strong as one wants, but we are getting very close to completely classify all static spacetime with lambda equal to 0. Okay. No, it's not so bad. So the theorem was already, I mean, a lot of people were happy with it, I guess. Yeah, the techniques are quite different from the ones one is used to. Is a lot of techniques that are intriguing techniques from comparison geometry, but also, I mean, asymptotically flat is a very natural physical hypothesis in this case as well. But in the static case, we are asking that so much that you expect that maybe you can do even better than you can even get rid of hypotheses that are in some sense natural anyway. Okay. So in any case, what matters is that in the case lambda, the message that I wanted to pass is that the case lambda equal to 0 is quite well understood. I mean, there are, of course, still open questions there as well, but we have a notion of mass, of total mass, which is already nice. This total mass has the properties that one expects, positive mass theorem and Pero's inequality. And in the case of static solutions, essentially we are able to classify all of them, provided some small hypothesis. Okay. In contrast, the case where lambda is different from 0 is much different. And I will focus in this talk to the case lambda positive, focus for the rest of my talk on the lambda positive case. Let me say a few words on the lambda negative case. So when lambda is negative, so the model is not the flat space anymore, but it is the hyperbolic space. But okay, they are not the same, but at least, I mean, you can hope that you can find a definition of asymptotically hyperbolic manifolds, and in fact, there is one, more than one. And you can hope that for asymptotically hyperbolic manifold, you can define a mass. And in fact, you can actually define a mass. And for this mass, you can prove a positive mass theorem in some cases, which are reasonable. I mean, there's a bit more work because there's more asymptotics that are possible. So for some asymptotics that are the one corresponding, I mean, are the one you expect, the mass is positive. And there are some other cases. Well, maybe let me draw a picture. So when you deal with asymptotically hyperbolic, so in the case lambda negative, you have a notion of asymptotically hyperbolic. So you have the hyperbolic space, and asymptotically hyperbolic means exactly what you expect. So some compact domain where everything can happen, and at infinity, you are like an hyperbolic space. But if you're asking for hyperbolic spaces, you can actually write some more where the cross section is stranger. So where you have like some genus here. So it's trickier because there are more asymptotics to consider. And for this kind of asymptotics, the standard one, where the cross sections are spheres, here we have a positive mass theorem as well. Here the mass is defined, but it is not positive, and there are examples where it is not positive. However, curiously, there's a Riemannian inequality that is known to hold for negative masses. So in this setting here by Lee and Neves. So there's work by Krushel, Herzlich, Wang, and Zhang on the positive mass theorem here, and there's work by Lee and Neves on the Riemannian inequality in this setting here. And using these results, they are able to prove some static uniqueness as well. So from the positive mass theorem here, they prove uniqueness of the hyperbolic space, essentially. So the hyperbolic space is a static solution, and it's called the anti-de Sitter in this framework. Or maybe you're familiar with it. and it is the only one that has it is asymptotically hyperbolic, and there's no boundary. Okay, but when there's boundary, there are plenty of solutions I mean, there's something similar to the Schwarzschild solution, the anti-Zeta Schwarzschild solution, and there's no uniqueness for that at the moment. Conversely, for negative masses, there's some uniqueness for some static solutions with negative mass using the Lee-Neves result. But I will not go in the details in this topic, so I will probably just cancel this out because I don't have time to give the details, but I mean, just to give some to give you a taste of what the lambda negative case, what is known about the lambda negative case. So there's a lot of gaps to be filled, but I mean, at least we have some understanding of what's the right direction to go on. Conversely, the case lambda positive, but there's not much to hang on to. And one of the reasons for it is that here the model that you expect is the sphere or the hemisphere. So now the model is not the flat space, it's not the hyperbolic space, it's just an hemisphere, S plus 3. And there's no end here. It's a compact manifold. Okay, so there's a very big difference between this case and the other one. I mean, in the other cases, you were trying to detect the mass at infinity. Here, there's no infinity. So you have to get a mass somewhere else. And so far, there's no accepted, I mean, there are some attempts, but there are no accepted definition of mass in this framework here. And in fact, even more, there's a conjecture by Binu that I want to mention here, Binu conjecture, that in some sense is trying to replicate a very special case of the positive mass theorem. So the positive mass theorem was telling us that the mass is not negative in the lambda equal to 0 case for asymptotically flat manifold. And it was telling us that when the mass is 0, then the solution is the Euclidean space. So we don't have here a notion of mass, but what Binu tried to do is the following. I mean, the heuristic is the following. So what does it mean to have mass 0 here? And what should mean to have mass 0 here? So Binu conjecture works as follows. So let's assume, so from now on, just for simplicity, lambda is equal to 3. It's not really important, the exact constant. So let's just say that lambda is equal to 3 from now on. And let's assume so that the scalar curvature is greater than 2 lambda, so it's greater than 6. Okay, so this is the standard natural assumption that we were expecting. I mean, this is the assumption that we started from earlier for the whole talk. And so we have, let's assume that the metric on the boundary of the hemisphere is just the standard metric on S2. Okay, and finally, let us assume that the boundary is totally geodesic. So this is the natural physical assumption that we always ask. So here we are. Maybe I should write this setting here. So we are taking the hemisphere, and we are taking a metric on the hemisphere. That is not necessarily the standard metric, the standard spherical metric. Okay, let's assume that this curvature is greater or equal than 6. Let's assume that on the boundary the metric is the sphere, is the spherical metric, and let's assume that the boundary is totally geodesic. So why these assumptions? So the first one is natural. The second one essentially is what one can expect to be the asymptotical flat hypothesis. So in the flat case, we were converging to the Euclidean space. Here, we should converge to the spherical space. And finally, this one should correspond to 0 mass. So we don't know what the mass is, but the mass measures how fast we are going to the Euclidean metric here. So here you should measure how fast we are going to the spherical metric, and this should correspond to the derivative in the normal direction to be 0, which is essentially the asking that the boundary is totally geodesic. Okay, so these are kind of the standard framework of the positive mass theorem in the rigidity case, and you would expect that under this hypothesis, the solution should be just the standard spherical metric on the hemisphere. This is the conjecture, and this unfortunately is also false. That has been proven to be false by a work of Brando, Marquez, and Neves. We used some gluing construction to actually glue a piece of the standard sphere with something else inside. So on something close to the sphere, you're actually exactly the sphere, close to the hemisphere, close to the boundary, you are exactly the sphere, and then inside you are perturbing stuff with keeping scalar curvature greater or equal than 6, and so you find a family of counterexamples to this conjecture. So there's no notion of mass here, and there's no notion, there's not even a notion of mass equal to 0 in this case. I mean, it's really open. And what about static? So in the static framework, what is known is that we have some solutions that are known. So, I mean, the standard hemisphere is a static solution. So S3 with this standard metric. This is a static solution. Then there's an analog of the Schwarzschild solution. There's an analog of the Schwarzschild solution. It's called the Schwarzschild solution. So it has two boundaries now. So there's two boundaries here where u is equal to 0. And I mean, let me try to give some more information because this will be helpful later. But so u is equal to 0 at the two boundaries, and then it's growing, and somewhere in the middle, you will have a set where u gets its maximum value. I mean, it's not really. So, okay, and let me write down the equations here as well, at least. So this is defined on some interval r minus r plus times S2. So this is the manifold. The metric is dr squared divided by 1 minus 2m over r plus r squared. And u is the square root of 1 minus 2m over r plus r squared. So it's kind of, if you remember, it's kind of like the Schwarzschild solution, but you have this additional term here, okay? And in order for this quantity to be positive, you cannot choose, wait, did I take this? This is a minus, okay? Before I, yes, of course. My memory is always bad. So minus r squared. Now everything works as expected. So there's a minus r squared. So this is negative a lot out of time. So in order for this to be a positive quantity, one needs m, the coefficient m to be not so big. So this is defined only for masses that goes from 0 to 1 over 3 square root of 3. So once m is in this range, then you have a solution that is shaped like that. And this is the formulas for G, U, and the manifold M, which is defined between two radii, R minus R plus, which correspond here R minus and here R plus to the two boundary components. So when M goes to 0, this black hole, this horizon is kind of expected to be the black hole horizon, shrinks, and you get the de Sitter solution. And when the mass goes to 1 over 3 square root of 3, you expect this boundary to enlarge, until eventually you get a full cylinder. And this is called the Nari solution. It's essentially a cylinder with a cylindrical metric, essentially. Okay, so this is called the Nari solution. So these are the three model solutions, and they are the only ones that we know. So there are not many solutions that are known for lambda positive, but it is not known if these are the only ones. So there are only very partial results on this respect. So there's some works of Kobayashi and Lafontaine that were able to prove that this is the case under locally conformally flat assumption. And there's a work of Ambrosio recently where he finds pinching conditions that allow him to conclude the same result, and also a bunch of other geometric consequences for vacuum static spacetimes with lambda positive. But still, the question of whether these are the only ones is still wide open. Yes. I don't know if maybe I didn't give the exact names. Maybe I should. I mean, this is the de Sitter, which is the hemisphere. This is the de Sitter Schwarzschild. Exactly. Yeah, I should have written it. Yeah, thanks. Okay. Yeah. Good. No. Yeah. See, this corresponds to the flat solution, so to the Euclidean space, and this corresponds, in some sense, is like the Schwarzschild solution, but instead of opening up to become flat, it closes again to another boundary. Yeah, that's. Yeah. Okay. So to summarize, in the case lambda equal to 0, we have a very good picture. We have a positive mass theorem. We have a Riemannian inequality, and we have a black hole uniqueness theorem. Here we don't have anything like that. And so, in what remains of my talk, yes. Yeah. Both are limit. Yeah, exactly. Yeah. It's not completely trivial because if you just, I mean, the Sitter, yes. I mean, if you take M to go to 0, I mean, you get exactly the formula for the Sitter. Exactly. Now this is slightly trickier. So if you take naively that limit as M goes to the maximum value, 1/3√3, then the two radii for which these things is well defined, they tend to coincide. Yeah, so they are shrinking, and so at the limit, everything just disappears. Okay, and this is not really a problem of the. I mean, it's not really the geometry that disappears. The problem is just a coordinate problem. So everything, if you rescale appropriately, then you get the radii. Exactly. Okay. So, in what remains of my time, which again I might ask again how much time I spent so far. I have well, okay. Okay. Yeah. But, I mean, there's a coffee break later. So. Okay. No, that's perfectly fine. So I will just kind of, I mean, I will finally talk about some of my research together with Lorenzo Mazzieri and Piotr Krushel. So what we did essentially is try to tackle the lambda positive case. So let me try to write down essentially, I mean, let me lay down the ideas, and then that's the most important part. Let's start with any static solution. So you get a static solution. Yes, which, yeah, good point. Yes, I might want to write it down. Yeah. Yeah, no, this was not. Yeah, thanks. Yeah, this is. Yeah, I might write it down again. I mean, it's not written here. Minus 3UG. Laplacian of U equal to minus 3U. So now the cosmological constant is 3, so these terms appear, and u is equal to 0 on the boundary. And let me discuss this problem a little bit more. Let me give you some easy information that you can get from this system. So if you just trace the first equation, and you use the second one to write down the Laplacian, you just get that the scalar curvature is equal to 6. Okay, so here scalar curvature is exactly 6. It's not just greater or equal than 6. Scalar curvature is equal to 6. The second information that you get, if you plug in u equal to 0, so on the boundary, if you plug in u equal to 0 here, you get that the Hessian is equal to 0 on the boundary. And from this information, it's relatively easy to deduce that the norm of the gradient of u is constant on the boundary. Okay, so and once you have this information, you also get that the boundary is totally geodesic. Okay, so you get a lot of information on the structure of the boundary, especially, and also on the scalar curvature of the whole manifold. Okay, so let's take a very general static solution. So let's say you have a solution to that problem over there, and we want to prove that this is actually a Schwarzschild solution. So we want to prove that this one is actually this one. Okay, so we take a Schwarzschild solution with some mass. Okay, what's the mass we'll discuss in a moment. But so the Zeta Schwarzschild. I said Schwarzschild. Yeah, the Zeta Schwarzschild. Yeah, two boundary. Yeah, thanks. And so the first thing that we check is the set of the maxima. So here in Schwarzschild Zeta, as I mentioned, u attains its maximum value somewhere in the middle, in some sphere in the middle. Okay, here the set of the maxima can be wild in principle. We proved something together with Lorenzo and Crucial, telling us that the set of the maxima is not that bad, is a stratified some manifold where the maximum stratum. So if there's some surface inside, that must be smooth and closed. Okay, so we actually assume that there is so that the maximum stratum is not empty. Okay, so that there's some surface of maximum point inside, and since we are asking stuff, we also ask that it's decomposing our manifold into two pieces. Okay, so I'm trying to describe this setting, the framework in which we get the best result. So let's assume that the set of the maxima here is big enough. So there's some surface inside, and this surface is dividing our manifold into two pieces. Then there can be other, I mean, it's not really important if there are other points or lines of maximum points. It's important there's something that splits our manifold into two pieces that we call m plus and m minus. And they should correspond to these ones. Okay? So what we ask is that the surface gravity here, which is, I will not go in the details of this as well, but if you take the norm of the gradient of u, I said it's constant. You divide it by the maximum of the value of u on the manifold. This division is essentially a way of rescaling, of fixing this as an invariant of the boundary and not making it. I mean, if you don't write this up to a normalization of u, you can make this quantity be whatever you want. This gradient of u. So this way, this is invariant under rescaling of u. Okay? So you consider this quantity, which is constant on every component. You take the maximum of it, and you call it k minus, the maximum of the surface gravity of the components. And then you do the same here, and you get k plus. Okay. Then you compare the values that you get with the Schwarzschild de Sitter solution. So here, for Schwarzschild de Sitter solution, you will have a value here, which depends on m, and a value here, which depends on m. Okay? And it turns out, and we can prove it, that whatever the manifold you take, I mean, whatever piece you have, you will find a Schwarzschild de Sitter solution, a region of the Schwarzschild de Sitter solution you can compare with. So there's a single value of m here or here that corresponds to that value that you computed for your solution. So from this, k minus, okay? That from this k minus, you have a way of computing the mass, okay? And from this k plus, you have a way of computing a mass. Let's call it m plus and then minus. And so let me say it again a bit clearer. So, and also, let me do it a bit more precisely. Since I guess I have the time to spend here a moment. So let me just write down the assumption that we need for everything to work precisely. I don't want to be completely general, but so if you ask that k plus is greater than square root of 3 and k minus is less than square root of 3, that k plus is less than square root of 3, that k minus is greater than square root of 3, what we can prove is that there is a value of m here for which this one corresponds to that quantity here. So there's a single value of m that corresponds to this value, okay? And we call it m minus. So we will compare it. We will compare this piece with this piece of the Schwarzschild solution with mass m minus. The same we do here. So if we start with k plus less than square root of 3, then there is only one choice of m for Schwarzschild solution, such that this region here has the same surface gravity. So we call that mass m plus. Okay, so there's we have a way to give a mass to the single pieces. And so what we ask now, lost my piece. Okay, so the theorem, let me state the theorem here. So in this framework here, if we, well, I probably didn't write down. Yeah, I didn't write down. Okay, so so we ask that k plus is less than square root of 3, and we ask less or equal. K minus is greater or equal than square root of 3. And finally, we ask that m plus, I don't remember the sign, I guess m plus is less or equal than m minus, should be the right sign, which I didn't write down. So under this hypothesis, and under the hypothesis that we are splitting the manifold into two pieces with the set of the maxima, then we are Schwarzschild ordinary I. So this is essentially one of the main theorems we did with Lorentz and Krushchev. I wasn't maybe perfectly clear on what I mean, but yeah, essentially, if we have two regions and these regions behave nicely, the surface gravities behave nicely, so they can be compared with the Schwarzschild solution. And if we have the right comparison between the two masses that we get from this comparison with the Schwarzschild solution, then it's definitely a Schwarzschild ordinary solution. And if I have the time, I'll give two words about the proof. If I don't have the time, I'll stop here. Okay, I'll take some minutes just to say a few words on how you actually prove this result. So the first step is to define a couple of functions. So we consider the function w, which is grad u squared. So why this function? Because it behaves now nicely on the boundaries, because the gradient is constant on the boundary, and it allows us to get an elliptic inequality through the Bochner formula, essentially. So this is essentially why one wants to consider this quantity here. And also, it also behaves nicely on the set of the maxima, which is also nice, because the gradient is just 0 there. And the second quantity we consider is is the same quantity computed on the model solution. So on the model solutions, the gradient, so here, the gradient of u, the norm of the gradient of u squared is a function of u. So on each level set of u, the gradient is constant. It's constant, yeah, it's the same value. So it's just a function of u. So we can do the same on a general manifold. So we take the value of u and we compose it with this function omega. Okay. So this gives a function on our manifold that replicates what happens in the model solution. Notice that we have two choices of omega. We can take omega minus here, or we can take omega plus here. There's two ways to compare the gradient with the function u. Okay? And we will use, of course, omega plus when we work in m plus, and omega minus when we work in m minus. Okay. So now that we have defined w and w naught in both regions, we write down an elliptic inequality for w minus w naught. I will not write that down, but there's an elliptic inequality for w minus w naught, I mean, a bit trickier than that, greater or equal than 0, an inequality on which we can apply the maximum principle. Okay. There's some tricks here because some things degenerate, so there's some work to be done. It's not trivial to find this inequality and then to prove that you actually can apply the maximum principle there, but you can, and you get that w is less or equal than w naught on the whole manifold. So you do it separately on m minus and on m plus, and this w naught is defined with respect to omega plus or omega minus on the two regions. Okay, so this is the crucial step. So once you get this gradient inequality, there's a lot of things that you can try to do. And the method that we used is to compare w and w naught close to this maximum set. So if you go close to the set of the maxima, what happens? So you can write down the expansion for w divided by w naught. If you write down the expansion of w divided by w naught for both choices, of plus and minus, you get this 1 plus 4 divided by 3 square root of 1 divided by n plus or minus, depends which one you're considering, to the power of 2/3 minus the mean curvature of this surface sigma, the surface of maximum point, divided by 2 times r, which is a sign distance. So it is positive on n plus and it's negative on n minus. Great. And so since we know that this quantity is less than 1, okay, because that's what we proved above, so this implies that we have an estimate on this quantity here. So we get that this quantity has a sign, and it has a different sign depending on if you are on n plus or if you are on n minus. So you actually get a double inequality. So you get 1 over n plus to the power 2/3 minus 3, less or equal than h of this, I'm calling sigma the red surface there, one of them, h sigma divided by 2, less or equal than square root of 1 over m minus the power 2/3 minus 3. So if you plug in our hypothesis on n plus and minus, that's been chosen so that this is greater than the other one. So the only way for this to work is that everything is an equality. So you get that m plus is equal to m minus, and that h is constant. And you can actually, and the constant is this one, square root of 1 over. Great. And so if you plug this information here and you expand to second order with this in mind, you get that w over w naught is equal to 1 plus 1/2 the norm of the traceless second fundamental form of sigma r squared. And since this is positive, and what we know that this is less or equal than 1, we get immediately that the second fundamental form is 0. And then, so we get a lot. We get that the second fundamental form is 0. And then from this, and the constraint and the Gauss-Codazzi equation, you get that the scalar curvature of sigma is constant. And so since the surface and the scalar curvature is constant and positive, you get that this is a sphere. So once you get that sigma is a sphere, then you write down your equations on sigma, and you use Cauchy-Kovalevskaya. It tells you that there's only a way to evolve your static equations starting from a sphere, and you know already what way it is the Schwarzschild way. So the solution must be Schwarzschild. And this concludes, I mean, the proof of this result. And so I guess the moral of the story is that the question is still wide open. This is an attempt of at least finding a uniqueness theorem in the case lambda positive. There are some hypotheses that we need to make. There's a mass that comes into play that we can prove that in the static setting as actually the hypothesis that we expect, like positive mass theorem, Riemannian inequality, even though I didn't go into details of that. But so in the static framework, there's a mass that we can use and gives us information on the static spacetime, so there's still a lot of work to do for all of you. So thank you for your time.
Thank you, Stefano, for this very interesting talk about this very fascinating topic. Are there questions for Stefano? Also from people online at home? Okay. I have a couple of questions actually. The first one is about the assumptions of this last theorem. Could you give us some hint about what are the philosophically optimal and what are the worst here? Because I didn't get it. So what do you expect? Where do you expect this theorem is not what you like, or do you think it's the best one?
Question. I mean, this is not even. We can somehow relax those hypotheses a bit more. So just for simplicity, I put k minus greater or equal than 3, then square root of 3, but that can be ruled out with some analysis that they want to get into. So it would be nice if we were able to get rid of k plus less or equal than square root of 3 as well. So that's something. I mean, we expect that it might be possible to rule out the hypothesis on k plus and maybe the hypothesis on the inequality between the masses.
Okay.
This, I mean, in principle, it's widely assumed that the only solutions are these ones. And a lot of people is convinced that this has already been proven.
Without any assumption.
Without any assumption.
Okay.
I'm not convinced. I'm not really convinced that this is the case. But so I guess if you ask something like that the set of the maxima is big enough, I will guess it's possible that it's possible. I mean, to prove this in full generality. I don't know how. I mean, that's,
okay. Thank you. And the other one is about something that you mentioned in the literature. Is not about this thing here because I didn't know that paper of Rieris.
Oh.
But is he assuming nothing about the asymptotic structure of the
in dimension 3? No, asymptotically flat. Yeah.
Okay, because I understood you said that Rieris was reaching the removal of the asymptotic flatness assumption.
Rieris. Sorry,
Rieris.
I heard Bray. No. Yeah, almost.
Nothing at all.
Completely removes it.
Nothing at all. Not even something very, very.
No, there's a first paper that he did some time ago where he proved that with some hypothesis, essentially on the topology at infinity, which is much less demanding, I mean, something on the continuation of geodesics at infinity, and the fact that the topology, I think he was assuming the topology was that one, like one
just the topology,
infinity. Then he was able to prove that the only solutions were the ones that were known. And then there's a couple of papers that are a bit more recent where he goes into quite a deep study of the, static solutions without any assumptions. And the only ones that he used, he uses some assumption. What he proved, let me say in 2 words. So he proved that, he said, first, there are a couple of other examples of static solutions that are known. One is a so-called boost. So it's a toric toroidal infinity, but it's very easy to write down. So it's, I don't remember how, but it's a very easy solution. It's just that it's not asymptotically flat, so no one writes it down. But it's something that is expected. And then there's another which is more complicated, which is I mean, you take a Schwarzschild solution and you take a lot of copies of it, and and there's a way to glue them together, and then you create a necklace of Schwarzschild de Sitter black holes, and so and this one is a static solution. So it has some kind of toroidal infinity as well. So
Okay.
and this is the family of Nicolai black holes.
So he had to, he has to add something in order to.
So he was able to prove that these are the only solutions, and the only the only caveat is this one. So he was able to prove. So the static solutions are Schwarzschild, flat, Schwarzschild, boost, and solutions that have the same asymptotics as the Nicolai black hole.
Okay.
So it's not really proven. He was able to prove then later in the axisymmetric case that to complete the proof. But it's not completely proven, but I mean, it's expected at this point that this should be the only one.
Yeah, exactly.
Yeah, that's,
Okay. Are there some other questions? If there are no other questions, we meet outside for the coffee break. So, and we can have a photo. Yes, we can have a photo together now. Here, well, at the coffee break spot. So thank you again, Stefano. Okay, it's a pleasure to introduce Giulio Colombo from the University of Milano Bicocca, who will talk about. No, it's Milano Statale. From the University of Milano Statale. Sorry. Who will talk about gradient bounds for the minimal graph equation on Riemannian manifolds.
Okay, so you're hearing me? Okay, it's working. Okay, thank you. I want to thank you, the organizers of this today conference, of this workshop, for this opportunity to present some results. And I will speak about, yes, gradient bounds and some applications of obtaining gradient bounds for this equation of Riemannian manifolds. And the result I'm going to present are obtained in collaboration with, are contained in several works and are obtained in collaboration with Edgar Susagana, Marco Magliaro, Luciano Mari, and Marco Rigoli. So I'm first going to recall the known classical results in Euclidean space as a motivation for possible generalizations on Riemannian manifolds, and to better justify why we are asking some questions and which lines of research we are going to pursue. So the minimal graph equation is the partial differential equation divergence of gradient of u over square root of 1 plus squared norm of the gradient of u equals 0. And it can be cast for a function u, a scalar function from Euclidean space Rm into R, or more generally, for a function u from a Riemannian manifold M into R. And in this case, of course, this is the gradient with respect to the Riemannian metric, and the divergence is with respect to the Riemannian metric. And okay, before introducing the classical results, I want to observe that this equation has a geometric meaning. That is, if U, in general, on a Riemannian manifold M, solves the equation, then the graph of U, which is a hypersurface into the product of M with R, is a hypersurface of a vanishing mean curvature. Then sigma has 0 mean curvature, when M cross R is endowed with the product Riemannian metric, so the Riemannian metric of M plus the standard Riemannian metric on the line, and I will use epsilon to denote the canonical coordinate on R, and G is will denote the metric induced on sigma by the ambient metric on the product. And the mean curvature, I briefly recall what the mean curvature is for a hypersurface, is the trace of the second fundamental form. The second fundamental form of the hypersurface is a tensor field defined as follows. If one considers x and epsilon, two vector fields tangent to sigma at some point, the second fundamental form is up to a sign, but I think that minus is correct, inner product between the directional derivative of the normal to the hypersurface in the point, at the point, the inner product between the directional derivative of the normal at the point in the direction of x contracted with the vector field epsilon. So for every y tangent to sigma, where n is the normal to sigma. Okay, and the mean curvature is the trace of the second fundamental form with respect to the Riemannian matrix G induced on the hypersurface from the ambient metric. And we say that a hypersurface with zero mean curvature is a minimal surface, a minimal hypersurface, because this equation is also the Euler-Lagrange equation for a functional, the area functional, and solutions of this equation actually minimize the area functional, at least in the class of graphs, in the class of hypersurfaces inside the product that can be represented as graphs of some function over M. So if U solves the equation that I just erased, and I will call in general MSE, minimum surface equation. If you solve MSE on Riemannian manifold M, then for every compactly contained domain into M that we will call omega, we have that the area of the graph of U over omega, which is given by this integral, is less or equal than the area of any other function, of the graph of any other function, say V, which shares the same boundary data as U. Okay. So, so the minimum surface equation is the Euler-Lagrange equation for this functional, and critical points of this functional are indeed minimizers. Okay, so they are actually minimal points for the functional, and so I can go to recalling the main classical results for the Euclidean space. The first striking result is the so-called Bernstein Theorem, which says the following. The theorem in its original form is due to Bernstein and was proved in 1955, if I remember well. and says that if U in 2 dimensions, so from R2 into R, solves the minimal surface equation, then U is an affine function. That is, the gradient of U as a vector-valued function is constant, and I want to say this in the following equivalent way: the Hessian of U is identically 0 on the manifold. So U is an affine function, and higher dimensional analogs of this theorem were investigated. The validity of possible higher dimensional analogs have been investigated for a lot of years, for nearly half a century. And then in the 60s, the following theorem was established by combined efforts from Fleming and the Giorgi, Allen-Cahn, and Simons. And it was, yes, a series of works in the 60s. If M is less or equal than 7, then every solution U from Rm into R of the minimal surface equation is affine. Okay, so as above, Hessian of U is identically 0. And the dimension 7 is sharp because the first counterexample was found by Bombieri, De Giorgi, and Giusti. We have that for every M larger or equal than 8 exists non-affine solution U from Rm into R of the minimal surface equation. First counterexamples due to Bombieri, De Giorgi, Giusti, and then Simon in the 80s produced a lot of other counterexamples by studying the behavior of solutions of this equation on exterior domains in Rn for general M. And okay, so this is remarkable. It was remarkable even in 1915, when Bernstein proved it, because this is a partial differential equation, and other partial differential equations, like the linear ones, for instance, Laplace equation, Laplace of U equals 0, have a lot of entire solutions defined on the whole space, on the whole R2, on the whole Rm, for any M. So this equation exhibits a strange and interesting rigidity property. Okay, and the property is connected to the fact that the surfaces, the minimal surfaces that are investigated, are representable as graphs over some hyperplane in the space, because you know that, for instance, in R3 there are a lot of complete minimal surfaces which are not planes. So it's a strange feature of this equation. And in 1961, a weakened form of the Bernstein theorem was proved by Moser, holding in any dimension, and is known as the Moser-Bernstein theorem. So for every dimension M, say greater or equal than 2, if U from Rm into R solves the minimal surface equation and has globally bounded gradient, so gradient of U, norm of the gradient of U is in L infinity of Rm, then U is affine. Okay, so if one a priori bounds the gradient of u, one obtains again the rigidity of the theorem, and in some sense this is not anymore so striking because if you compare, for instance, what happens to harmonic functions, okay, if you prescribe that a harmonic function, an entire solution of the Laplace equation on Rm has globally bounded gradient, again the function must be affine. However, the theorem holds in any dimension, and by a subsequent global gradient estimate due to Bombieri, De Giorgi, Miranda, the assumption on the boundedness of the gradient of u has been relaxed to control on the asymptotic behavior of u at infinity. That is, in 1969, Bombieri, De Giorgi, and Miranda proved the following. For any r, for any positive radius r, and for any x belonging to Rm with m greater or equal than 2, if u solves the minimal surface equation not on the whole Rm, but only on the ball of radius r centered at x, then the gradient, the norm of the gradient of u at the center of the ball, the point x, is less or equal than a constant, positive constant C1 only depending on the dimension of the manifold, times exponential of a second positive constant, say C2, times the value of the function at the point, at the center of the ball, minus the infimum of the function on the ball, divided by the radius of the ball. So this is a local gradient estimate for local solutions that is somehow scale invariant. Okay, it holds with a uniform constant for any radius r, and in particular, this estimate implies that if u has negative part of at most linear growth or positive part of at most linear growth, then it must have a globally bounded gradient if it is an entire solution of the equation on Rm. So I will briefly say, if one of those conditions is satisfied, that u has at most linear growth on one side. So I will say that u from Rm into R has at most linear growth on one side if either ux is larger or equal than minus a positive constant times 1 plus distance of x from the origin for every x in Rm, or the other possibility, u of x is less or equal than a constant times 1 to x for every x belonging to M. So if for some c, positive c, one has this. And if u satisfies one of these conditions, then one can apply the above gradient estimate either to u or to minus u, and one obtains that the gradient is globally bounded on the manifold. And if one pairs this with the Moser-Bernstein theorem, one obtains that for every dimension m, if u is solution of the minimal surface equation with at most linear growth on one side. Then U is affine. Corollary of the corollary, the Liouville property. If U is non-negative, then U is constant. Since non-negative function clearly has negative part of at most linear growth, and by this theorem it is affine, but having to be non-negative, it must be constant. This is the only possibility. And okay, so there are three properties that capture the attention. That is the validity of a Liouville theorem for this equation in any dimension, the validity of this weakened form of Bernstein theorem holding in every dimension, and the original Bernstein theorem that holds only in sufficiently small dimension. Starting from this, we are led to the following problem. On general Riemannian manifolds, where this equation can be stated and makes sense, what kind of geometric assumptions one could make on the geometry of M, for instance, on its curvature, to ensure the validity of similar properties. So the problem is, roughly stating, the following. Give conditions on complete. In general, it will always assume to be complete and non-compact. On a complete Riemannian manifold, so that one of the following properties holds. I start from the Liouville property. If U greater than 0 solves minimum surface equation on M, then U constant. More generally, if U solves MSE and linearly grows, at most linearly grows, on one side, then in general it will make no sense to say that U is affine, because on non-affine space, affine functions are not well defined. But I stated the Bernstein theorem at the beginning by saying that, by restating the affine condition in the equivalent way, saying that the Hessian of U vanishes. And this makes sense on any Riemannian manifolds. So the property can be stated as follows. If U solves and has most linear growth, then Hessian of U identically vanishes on M. And the third, harder and stronger property is the validity of the Bernstein theorem. So if U solves the minimal surface equation without any further assumption, then Hessian of U is identically 0 on a manifold. So the general idea, the general program is to identify some meaningful conditions on the geometry of the manifold M, so that at least one of these properties is satisfied. Clearly, 3 implies 2, 2 implies 1. So the classes of manifolds satisfying these properties will be encapsulated, boxed one into the following. And so far, we have been able to give interesting, in our opinion, answers, at least for conditions 1 and 2, while the problem of identifying meaningful geometric condition ensuring 3 is quite hard. and is essentially open. That is, I briefly say something about 3, is known to hold when M is parabolic and Ricci, the Ricci tensor is non-negative. Ricci is larger or equal than 0. And this is generally known, but I couldn't find a precise reference for this, apart from a work by Harold Rosenberg, where he proves this when M has dimension 2. So the case where dimension M is equal to 2. And note that if, I will come in to, okay, I will say it briefly. Okay, when dimension M is equal to 2, then Ricci non-negative means that the Gaussian curvature of the surface, because dimension 2 is non-negative, because this is the only component of the curvature tensor in that case. There are possible different definitions of parabolicity for Riemannian manifolds, but the one that we are interested in is the following. I state it for complete manifolds. So if M is complete, we say M parabolic if for every, say, C2 function over M, Laplacian of phi less or equal than 0 and inf over M of phi larger than minus infinity imply phi constant. So a manifold is parabolic in this sense if and only if the only lower bounded superharmonic functions are constant functions. Equivalently, if and only if upper bounded subharmonic functions are constant. And okay, this is not really a satisfactory response because, for instance, when one considers the Euclidean case, Rm is parabolic if and only if M is less or equal than 2. So apart from the one-dimensional case where the Bernstein property is trivial, this theorem only recovers the original Bernstein theorem. And so it's weaker than, even in Euclidean case, is weaker than the sharp result from the 60s. And maybe I'll sketch a proof of this. Yeah. Well, I expect, for the general Bernstein theorem, so the stronger property, I expect that the characterization also includes the dimension. So in general, one can expect that no negative curvature in some sense, but this is absolutely a guess. We don't know what could be true, that no negative curvature in some sense and dimension one would expect is again a dimension less or equal than 7 would imply that every entire solution is has vanishing Hessian, so it's essentially a fine. No, not exactly. That is, you can have parabolic manifolds with no negative curvature of any dimension. Okay, because, for instance, you can take a parabolic surface, which is a complete surface with dimension equal to, and take its product with a compact manifold of any dimension. What you obtain is again a parabolic manifold. So in this sense, no, parabolicity does not give any bound on the dimension of the space. Okay. And okay, so this is what, to the best of my knowledge, is known about property 3. While for the first and the second, we have the following results. One holds for any, so the Liouville property holds for any complete M with Ricci non-negative. And we proved this result. This was obtained by me and Marco Magliaro, Luciano Mari, and Marco Rigoli in 2 years ago, as a consequence of a global gradient bound, which I'm going to state now for, in general, for entire non-negative solutions on complete manifolds with lower bounded Ricci curvature, and also in the same days, we uploaded the preprints on archive in the same days by Kuding via a completely different technique. That is, he proved the validity of a global Harmonic inequality on minimal graphs over manifolds with no negative Ricci curvature, and more generally, manifolds satisfying a doubling condition and weak Neumann-Poincaré inequality, which are ensured, the validity of which is ensured on any complete manifold with no negative Ricci curvature. This is a consequence of the following theorem. If M is complete and has Ricci greater or equal than minus square of key for some constant key larger or equal than 0, and U is a non-negative solution of the minimal surface equation over M, then square root of 1 plus squared norm of the gradient of U is less or equal than E to the power he U. So this pointwise gradient bound holds on everywhere on the manifold, and clearly when t is equal to 0, so the manifold has a non-negative Ricci curvature, one obtains that this function must be less or equal than 1, and hence it must be identically 1, so the gradient of U must be identically 0, and the function is constant. And okay, so this is what concerns property 1. And about property 2, yes, in fact, there are a lot of examples. That is, for instance, if you consider the hyperbolic space, so negative constant curvature, there are infinite bounded solutions, entire solutions, non-constant entire solutions of the equation. And in fact, if you consider the hyperbolic space, for instance, with this, it's a Poincaré disk model, and so consider the boundary of the disk in the model as the ideal boundary at infinity. For any continuous function on the ideal boundary, you can solve the Dirichlet problem for the minimal surface equation, and you obtain a non-constant bounded solution of the equation. This has been proved by Ripoll and some other authors, but at present I don't remember them, sorry. Around 2000, and since then there has been a lot of works in general in solving the Dirichlet problem for asymptotic data at infinity on hyperbolic space, and in general on manifolds with negative curvature near the constant negative curvature of the hyperbolic space, so with pinching conditions on the sectional curvature, solving the Dirichlet problem for the minimal surface equation, for the constant mean curvature surface equation, and in general for prescribed mean curvature equation. So, so yes, we don't expect the validity of this kind of rigidity property on manifolds with essentially negative curvature. And concerning property 2, we have some results. One of them, maybe the most neat one, is the following. Property 2 holds for any complete M with non-negative sectional curvature. Okay, and let me briefly say what's the idea behind the proof of this theorem, because in fact we are able to prove something more for manifolds where only Ricci is non-negative. In fact, this is a consequence of essentially two new results that are the following ones. First, we have a local gradient estimate for solutions on manifolds with non-negative Ricci curvature and sectional curvature bounded from below by a negative constant. So if M is complete, has Ricci non-negative, and sectional larger or equal than minus t squared for some constant, some non-negative constant kappa, and U solves the minimal surface equation on some geodesic ball inside M, then we have a gradient estimate of exponential time. We have that the square root of 1 plus square norm of gradient of U x is less or equal than positive constant C1 times exponential of a positive constant C2 times M times T times value of U at x minus the infimum over the ball of U divided by R squared. Okay. With say okay, in fact, the estimate is this one. So if key is larger or equal than 1, you have key. Otherwise, you can have 1, because otherwise the estimate would fail in general. And C1, C2, not depending, say absolute, not depending neither on the dimension or the curvature constraints. So the dependence of this estimate from the dimension and the bound on the curvature of M's is contained in this term, essentially. So the bound on the sectional curvature is appears quantitatively in the estimate, but what we are interested in obtaining is boundedness of the gradient for solutions with at most linear growth on one side, and this is again ensured by an estimate of this form. So as a consequence of these, we have that if M complete reach non-negative sectional bounded below it from a negative constant, and U solves the minimal surface equation with at most linear growth on one side. Say the negative part of U is big O of the distance from a fixed reference on the manifold. Then gradient of U is globally bounded. And the second result that we obtained, and I'm going to state, is some kind of Moser-Bernstein theorem for for manifolds with non-negative Ricci curvature, and goes as follows: if M is complete with Ricci greater or equal than 0, and gradient of U is bounded, then every tangent cone at infinity for M, and U is non-constant, otherwise this is false. So I say U is non-constant solution of the minimum surface equation with bounded gradient. Then every tangent cone at infinity for M splits as a product of a line times a metric cone. Splits as line times a metric cone, say X. And how the general result for a manifold with non-negative sectional curvature follows from this by means of effect for manifold with non-negative sectional curvature, that is, for such manifolds, tangent cones at infinity splits in this way if and only if the manifold itself splits. This is a consequence of the Toponogov theorem, and it is found stated in a work by Kolding, Chigar, and Minicozzi on harmonic functions of linear growth on manifold with non-negative Ricci curvature, and it is stated without proof. I didn't know any proof of this until I read the appendix of a paper that recently was published on Archive by Antonelli, Fogagnolo, and Pozzetta, and Pasqualetto, if I remember well. Yeah, no, Eliabre, sorry. Sorry. And so we have this fact that if M has sectional greater or equal than 0, then tangent cones at infinity split if and only if M itself splits. So if and only if M can be written as a Riemannian product of R with some complete manifold N. Okay, so you combine the these statements, and you obtain that on the complete manifold with non-negative sectional curvature, a function with, say, negative part of most linear growth has globally bounded gradient. Then the gradient of u, if u is non-constant, provides a direction of splitting for tangent cones at infinity, and this implies the splitting of the manifold itself. So the proof is not, say, direct on the manifold. It involves this passage to the geometry at infinity. And if u is constant, instead, okay, it clearly has a Hessian equal to 0, and then one does not have any form of splitting, but the theorem, the statement of the theorem is holds. That is, the property 2 is trivially satisfied in that case. And we observed that the fact that in general, with non-negative Ricci curvature and bounded gradient, one only obtains some information about the behavior of tangent cones and not of the manifold itself is not a technicality, but it's a sharp result in some sense, because there are examples of complete manifolds with non-negative Ricci curvature and supporting entire solutions of minimum surface equations with bounded gradient that do not split in any direction, not only in a direction provided by the gradient of u, but in general, not in any possible direction. The general idea for the construction of the counterexample is the following. Consider manifold n with metric pending n, a complete Riemannian manifold. And consider a positive smooth function, say alpha, on n, and endow the product manifold n times r with the following word metric. Find m equal to n times r, and cast on m the metric of n, direct sum with alpha squared, the standard metric on the factor, on the linear factor, say the coordinate is dt, and consider the function u on the manifold M given by the coordinate function t. So u of xt equal to t. Then one has that the Hessian of the function u is equal to minus 1 over alpha, differential of alpha, tensor product, differential of u, and symmetrization, differential of u, tensor product, differential of alpha. So if alpha is not a constant function, this function does not have a vanishing Hessian. But if one writes the minimal surface equation in trace form, say, if you compute this divergence, you obtain the Laplacian of u on the manifold M divided by this square root, minus the Hessian of u computed in the direction of the gradient of u divided 1 plus square root of this gradient term to the power of 3. And this vanishes because the u is orthogonal to the alpha, because alpha only depends on the factor n, not on the factor t. So these metrics, the matrix of the Hessian of u has 0 diagonal components, so the Hessian is 0, and the Hessian is also 0 when computed on du, because du is orthogonal to the alpha. And so one obtains that u is in fact a solution of the minimal surface equation with non-negative, with non-zero Hessian. And of course, this is a counterexample if one is able to construct an example of such a manifold with non-negative Ricci curvature and with bounded function alpha, so that the norm of the gradient of u, which is alpha to the power of the -1, is bounded. And this is indeed possible and was done by Kazu and Washio in a work of 1990. And when they constructed this counterexample precisely to show that in general on manifolds with non-negative rich curvature, it is possible to have harmonic functions with bounded gradient that do not non-constant harmonic functions with non-negative bounded gradient that do not provide directions of splitting of the manifold itself. Yes. I don't know. I don't know if there's this holds in general. That is, you can make a bit more complicated expressions and still construct examples of function. Yes, that is, in general, the idea is this one. If you are able to construct a function whose Hessian has 0 diagonal components, and the components that are not 0 contains terms that are orthogonal to the gradient of the function, then you obtain something with non-vanishing Hessian, but with vanishing mean curvature of the corresponding graph. That is, it's a long computation, it's a subtle construction to obtain such an example with non-negative Ricci curvature. For manifolds more complicated than warped product, computations I think are far more length complicated. And so I don't know if someone has tried to construct some counterexample in general in that case, but it could be. I don't know if there is some kind of classification in this sense. So Kazu and Washio constructed example of such a warped product with strictly positive Ricci curvature and also Euclidean volume growth. So the maximal volume growth allowed by Bishop-Gromov comparison theorem. And the Ricci tensor is strictly positive, so not only the gradient of U cannot provide a direction of splitting, but in general, the manifold cannot split any line in any direction. So it's a sharp. And because of the existence of such a counterexample, the most I think that, or at least the most that we could say about manifold with non-negative Ricci curvature is that the bounded gradient implies a splitting of tangent cones at infinity. And then only for a sectional non-negative, we are able to say something on the manifold itself. I don't know how much time I have again. I still have. Sorry, 10 minutes? Okay. Then I will briefly sketch a proof, at least of the splitting theorem, of the results that lead to the splitting theorem. So, oh, okay, okay. So I sketch something more. Okay. Okay, no, let's say I'll speak again for, I think, 15 minutes and then is something else. And yep. Oh, sure, sure. Well, definition is the following. Say, sorry, okay. The general idea before giving the definition is this one. Take the manifold M with its Riemannian metric, say, this symbol, metric for metron M. Consider a diverging sequence of positive numbers lambda n. So and take rescalings of this manifold by multiplying the metric by say lambda n to the power of -2. Okay, consider the sequence of Riemannian manifolds Mn with metric n given by the original metric as manifold as a space of points, and lambda n to the power of -2, the original metric. Fix the point O in M, and then this point is also a point in any manifold Mn. Then you obtain a sequence of pointed manifolds that are in general triples, Mn, metric n, O. And this sequence is a sequence of manifolds if the original manifold M has lower bounded Ricci curvature, is a sequence of manifolds with pointed manifolds with lower bounded Ricci curvature and bounded dimension, because they all have the same dimension. And so up to a subsequence, it converges in the pointed Gromov-Hausdorff metric, pointed Gromov-Hausdorff topology, to some limit space, which is in general a metric space, but not a manifold, unless you put some additional constraints on the geometry of M, for instance, bounded geometry. So if Ricci of M is larger or equal than 0, then Mn metric of n not subconvergence in the pointed Gromov-Hausdorff topology to some limit manifold, say limit space M infinity. In general, it is only a metric space, so you don't have a Riemannian metric, but only an instance, and some point, say O infinity, okay? And what does it mean that this converges in the pointed Gromov-Hausdorff topology? There are possible different definitions, equivalent definition of this. I'm absolutely not an expert in this, so I'm sketching only very intuitive ideas. What does it mean? That you can find, if you look at it extrinsically, you can find a complete separable metric space fine, say if there exists a separable metric space, say Z, dz, such that each of these metric spaces is isometrically embedded in Z, and the limit space is isometrically embedded into Z. And for every R, positive R, the geodesic balls of radius R of Mn centered at O converge in the Hausdorff sensing, in the Hausdorff instance, to the geodesic ball of the limit space of radius R centered at O infinity. Okay, for every for every positive R, the geodesic ball, say B R in the metric, in the distance induced by the metric N centered at O, converges to the ball of radius r of the limit space in the Hausdorff instance in Z. And I think this is a viable definition of convergence, of pointed Gromov-Hausdorff convergence, but okay, I can expect to be contradicted if I forgotten something essential. And okay, so if this happens, then that object is in general a metric cone if the manifold has non-negative Ricci curvature. And is called tangent cone at infinity for the manifold. So it is in some sense what one obtains from looking at the manifold from infinitely fair. Okay, and okay, and I'd like to briefly sketch the main ideas behind the proof of the second result leading to the splitting theorem, that is the say asymptotic Moser-Bernstein theorem for manifolds with non-negative Ricci supporting minimal graphic functions with bounded gradient. Essentially, what we do is the following. We prove the validity of some L2 estimates for the squared norm of the gradient of U and of the Hessian of U on geodesic balls that resemble, or that is, they resemble because they were inspired by them, resemble the estimates proved by Kolding-Minikotzi in the case of harmonic functions, and then we use them to obtain the asymptotic splitting of the manifold. So in fact, what we prove is the following. If M is complete with Ricci non-negative and gradient U non-constant solves the minimal surface equation, minimal graph equation with bounded gradient, then for any fixed origin in M, one has that the limit as the radius r approaches plus infinity of 1 over the measure of the ball centered at O with radius r times the integral over the same ball of the squared norm of the gradient of U converges. This limit is equal to the sup on the manifold M of the gradient of U squared. And so the integral means of this function converges to the sup of the function, and the limit of r squared times the integral mean of the Hessian of U squared is equal to 0. So one proves the validity of these estimates, and then one essentially repeats the argument sketched by Kolding-Minikotzi in their work for splitting of manifolds supporting harmonic functions with bounded gradient, and one obtains the splitting of the tangent cone at infinity. That is, the details are technical. One uses this estimate to prove that the functions un on the manifolds n defined by taking the original function u and dividing it by Allen, one proves that these functions subconverge locally uniformly to a limit function u infinity on the manifold M infinity, which is a Lipschitz function. And the functions UN are not harmonic. Okay, so one cannot conclude that this function is harmonic because it's the limit of a sequence of harmonic functions. But these functions have controlled the gradient and the Hessian in an integral way, and one observes that the Laplacian of a function U can be controlled in this way, but by the squared norm of the Hessian of U. So in fact, the Laplacians of these functions converge in the L2 sense to 0, and that is enough to obtain that the limit function U is in fact harmonic. And what one obtains is that U is harmonic on the limit space, that the gradient of U on the limit space, or to be more precise, the slope of U defined as the lim sup of the incremental ratio around the point is constant, different from 0. And this is enough to obtain that the manifold, the space M infinity splits along the direction of what happens to be the gradient of U, because one obtains that the Hessian of U infinity is equal to 0. This is done in for when the functions UN are harmonic in for instance, in a paper by Brouet, Pasqualetto, and Semola from 2019, and the argument essentially repeats their argument apart from this observation for this minor modification, and the fact that this implies the splitting of the space M infinity has been given, for instance, in work by Antonelli, Brouet, and Semola, if I remember well. There is a question. It can be wild. In general, it can be, yes, in general, it is not a manifold. It is also not unique. That is, it can depend on the sequence of rescaling that you consider, and also on the base point O that you fix in the manifold. Harmonic in the distributional sense, in the in the weak sense, in the variational sense, if I'm correct, but maybe I can be contradicted. That is, you define the harmonicity of U essentially by defining an inner product on symbolic gradients of functions on this limit space, which are in themselves defined in terms of the Chigger norm of the function that exists if we are on an RCD space in general, that is a CD space that is infinitesimally Hilbertian, and then you can define an inner product between gradients of a function, or to say it more precisely, the integral of the inner product between gradients of functions, and then you take that, you use that to give a definition of harmonicity essentially by integration by parts, symbolic integration by parts. You can say this. Yeah. No, do not ask for Euclidean volume growth, and first, we proved it with some restrictions on the growth of the volume of the manifold, because we wanted to parallel the proof of these inequalities given by Chigger, Golding, and Minikotz in their paper, and then we wanted to use the distance functions as a cutoff function, and then to control to suitably control the Hessian of the function. We needed some additional assumptions on the growth of the manifold. But then we observed that in general one has the validity of the following result. If M is complete with non-negative Ricci and L is a uniformly elliptic second-order differential operator in divergence form, so say L of phi is defined as the divergence of A acting on the gradient of phi with the symmetric matrix A satisfying the pinching condition that is something like this. If L is a uniformly elliptic operator in divergence form and F bounded satisfies L of F larger or equal than 0, then the integral means of F over both the center at any origin converge as R goes to plus infinity to the sup on the manifold M of F, and R squared over volume of BR times the integral of LF converges to 0 as R goes to plus infinity. So why this gives this? Because if U has a bounded gradient, then the graph Laplacian of the graph of U inside the manifold M times R is a uniformly elliptic operator, and one has that the function okay, I write it down and then I say if gradient of U is bounded, then the graph Laplacian, so Laplace-Beltrami operator, of the graph sigma with metric G is uniformly elliptic. And one has the validity of Jacobi equation. And in particular, if you define the function W as a square root of 1 plus square norm of du, satisfies Laplacian G of W larger or equal than the squared length of the second fundamental form of the graph times W. That is Laplacian G of W is equal to this plus non-negative terms involving the Ricci curvature of the space and the squared norm of the gradient of W. And one can observe that the second fundamental form of the graph is essentially given by the Hessian of the function U. So one can further estimate this, if I remember well, as squared norm of the Hessian of U. This is the norm taken with respect to the metric G, while this is the squared norm with respect to the base metric on M. This times w to the minus 3. So, in particular, if one considers the operator as operator L, the Laplacian, this Laplacian, then the function w is subharmonic and is bounded, since the gradient of u is bounded. In particular, w to the power of minus 3 is bounded away from 0. So this is larger or equal than a constant, a positive constant times the squared norm of the Hessian of u. And then one puts this into the second estimate and obtains the L2 estimate for the Hessian of u at infinity. And concerning the gradient of u, one observes that the gradient, the squared norm of the gradient of u can be written as w squared minus 1. So if w is L subharmonic, then also its square is subharmonic, and its square minus a constant is subharmonic. So this is also subharmonic. And okay, and then one takes as function f the function gradient of u squared and puts that into the first inequality, and one obtains the L2 estimates for the gradient of u. This estimate has been this mean value inequality, this limit behavior of the mean value inequality for subharmonic functions was first proved by Peter Lee for the Laplacian on manifolds with non-negative Ricci curvature, while this one is essentially contained in the paper by Cigher, Kolding, and Minicozzi. They implicitly use it, that is, they prove it for the only case that they are interested to consider, but in general the proof works for the Laplacian applied to any bounded function f. And the generalization to uniformly elliptic operators, to the best of our knowledge, is new, and is based on heat kernel techniques, essentially. So the proof of the first parallels the proof by Peter Lee, which uses the heat kernel for the Laplacian. And the second one uses modified heat kernel as a cutoff function instead of the distance function used in the original proof by Cigher, Kolding, and Minicozzi. And it is needed to have something with control Laplacian for the proof of Cigher, Kolding, and Minicozzi, because they essentially use the green identities over bounded domains to obtain their estimates. And so one needs something with L, a cutoff function with L applied to the cutoff suitably controlled, and the distance functions is not suitable to do this unless one requires some additional conditions, for instance, of the Schwarzschild curvature of the manifold. And so we needed to find a different way to obtain it. Okay, I think I'll finish here my talk, and I thank you for your attention. Thank you. Thank you.
Thank you, Giulio, for this very, very interesting talk. There's time just for fast questions, and if there are any, please, Gioacchino.
Yes.
Oh, please.
Thank you again for the talk. Just something to be sure. Since you never used the Euclidean volume growth assumption, you confirm me that you never used the structure of cone on the.
Yes.
So you just use that they are Ricci limit spaces, the asymptotic cones and LCD spaces. So you never use that you need a cone.
No.
Cone.
That is the limit space is only taken into account for the limiting result. That is, once you have the L2 estimates, then you can prove the splitting. But the validity of these estimates does not involve any asymptotic behavior of the manifold. It's only based on estimates for the heat kernel associated to the operator L, which is indeed proved by adapting some gradient estimates that are derived from work of Saloff-Coste for uniformly elliptic operators on Riemannian manifolds with non-negative Ricci curvature, or in general Ricci curvature bounded below from a constant, by a constant.
Okay, thank you.
Thank you.
So we resume with the last speaker. I should not fail the affiliation this time because we have Fritz Hiesmayr, who is a new colleague of mine here at the Centro de Giorgi. He arrived in Pisa some days ago, so welcome Fritz also in Pisa. And he will talk about the Allen-Cahn equation and minimal surfaces. So thank you, Fritz, for having accepted our invitation, and please go on.
So let me respond to your kind words by thanking you for the invitation. I admit it's been a while that I've spoken in front of people in person, but it's good to be back. So the topic of my talk is the Allen-Cahn equation and its relationship with minimal surfaces. One other thing I should say is that I want to thank the audience as well, both offline and online, and I want to encourage you to ask questions at any time during my talk. Yeah, so then you're more than welcome. So in terms of an overview of my presentation, it's split into basically 3 parts. In the first one, I want to draw a general picture of defining the Allen-Cahn equation and sort of giving an impression of what its relationship with minimal surface theory is, with sort of an emphasis on the asymptotic behavior of sequences of solutions of the Allen-Cahn equation. So the second part, I will discuss variational properties. I will define what I mean by the Morse index of solutions of the Allen-Cahn equation and for minimal surfaces. Motivated, so the results of these sections are motivated by the construction of minimal surfaces, minimal surfaces by variational min-max arguments. And so in the last part, I will specialize to results that are valid in the round 3 sphere. This is sort of a very specific situation for several reasons, sort of due in part to the curvature of the 3 sphere. So the Ricci curvature is positive, and in other part to the symmetries and the isometries that act on this manifold. The motivating question that I hope we'll eventually get to is the question of sort of characterizing the solutions of the Allen-Cahn equation in S3 that have a small Morse index. Yeah, so this is sort of the eventual aim that we can keep in mind for the presentation. So one last thing I should say before I start the presentation proper is that I've tried to make the presentation more accessible by maybe sacrificing something in terms of the sort of the sophistication and sort of a precision of what I'm stating. So I hope that's been successful, and really I want to encourage you to ask any questions if anything is unclear. Yeah, especially the people sitting in the back. Yeah, you know who you are. Yeah. Okay. Okay. So what is the Allen-Cahn equation? So it's a semilinear PDE depending on some small parameter epsilon. The unknown of the equation is a scalar valued function u. So this is defined on domains in a Riemannian manifold. Actually, for us, in order sort of to avoid technical complications related to boundary values, most often this will be defined on the whole manifold. so you'll notice the equation is semilinear because the highest order term is just the standard Laplacian, weighted by this parameter epsilon. So I mean, the reason why this equation is semilinear rather than purely linear is this nonlinearity W prime of U. Yeah. So W here is a so-called double well potential. Double well because it has two minima at -1 and 1, yeah, with a maximum in between them. So the precise form that the function W takes is less important, but sort of a standard formula that is used is this that is given here, namely this WT is 1 minus t squared, the whole thing squared. Yeah. So if you want to, you can assume throughout that this is what we're taking. So you can see from the form that the equation takes is that there's some sort of trivial solutions that you get for free. Yeah. So if you take the constant functions plus and minus 1, then these being critical points of W, these are sort of solutions that are readily available. The next sort of trivial observation is that by an application of the maximum principle, yeah, any regular solution will have values strictly contained between those two bounds. Yeah. Sort of in historical terms, what I wanted to say is that the Allen-Cahn equation originates in physics. Yeah. So what they were trying to model or represent with this equation are sort of a phase transition phenomena, where you have a medium composed of two different metals. Yeah. So in this analogy, U would sort of represent the relative densities of these two metals. Yeah. So you'd have what you would observe is that there's two domains where U is basically purely of one or the other component, with a small transition layer between them. Yeah. So basically, you can consider your manifold split into two parts. One where U is roughly -1, the other one where it's 1, with this thin phase transition between them. So on the left-hand side, I've illustrated the behavior of a solution if you were to consider this equation on the real line instead. Yeah. And this also sort of models the transition between the two values. Yeah. So on the left-hand side, U would be basically strictly equal to -1, and on the right-hand side, U basically be equal to 1. Yeah. This transition layer that I've indicated with the dotted lines would depend on the parameter epsilon, and as we eventually let epsilon go to 0, this transition layer will also go to 0. Yeah. Okay, so let's consider this equation from a variational point of view by defining the Allen-Cahn functional. You recognize again that there's two different terms. One kinetic term with the gradient of U weighted by epsilon, and the potential term that's weighted by its inverse. So this is exactly, so I mean, the PDE that we saw on the previous page is exactly the Lagrange equation for this functional, which means that U solves this PDE if and only if it's critical for this functional. So let's try to see where eventually these minimal surfaces come from. So let me give sort of a slightly sketchy calculation. So there's sort of 3 steps involved here. In the first line of my calculation, I am bound below my functional using an arithmetic geometric mean inequality. Yeah? There you see that the two sort of inverse weights of epsilon and its inverse compensate for one another, yeah, and disappear. The fact that we have a gradient term in on the right-hand side of the first line, it's advantageous for us because it allows us to apply the co-area formula. Yeah. So instead of integrating over m, we can integrate over the level sets of the function u. Yeah? So the one sort of really sketchy part is the last line, yeah, where I basically sort of ask you to assume that the n-dimensional area of the level set that we're considering is comparable to that of the zero set, yeah, the nodal set of u. If you're willing to sort of make that approximation, then you can see that the energy functional basically splits into a factor of two things. First of all, the area of the nodal set, and second, this universal constant expressed as an integral. Yeah, notice that here this integral doesn't depend on u. Yeah, so this is just some sort of some constant. So obviously this is a little bit sketchy, and it's sort of it's contingent on two things. First of all, we want this inequality in the first line to be closer to being an equality. Yeah, so that means that we want the kinetic and potential energies to be comparable. Yeah. The second thing is that we want these areas of the level sets to be similar. Yeah. If both of these things applied, then this calculation would be justified, at least on a sort of a semi-rigorous level. Yeah. So maybe we'll come back to that at a later point. So maybe one thing before moving on is that sort of if you accept this this sort of proposition that the energy functional of u is comparable to the area functional of its area, then u being critical for the energy would sort of imply that its zero set should at least be close in some sense to being critical for the area. Yeah. So this is where minimal surfaces come in. So we already saw these a couple of times, but let me remind you the definition again. Yeah. So any sort of a surface is called minimal if it's a critical point for the area functional. So the definition of this is defined in terms of the flow of some vector field. Yeah. So if you deform sigma according to this vector field x, and you look at the variation of the area at the linear order, yeah, you can express this either in terms of the divergence of the vector field over sigma, or in terms of its mean curvature. Yeah. So a few comments on this. For us, we'll exclusively consider codimension 1 surfaces. Yeah. So this is basically the same sort of, for instance, one might have a 2-dimensional surface in a 3-dimensional manifold. The second comment I want to make is that if you look at the definition, although the characterization in terms of the mean curvature and the one in terms of the divergence are equivalent if you're working in the smooth category, the advantage of working with the divergence expression is that it allows you to generalize to less regular settings. Yeah. If you work in sort of the variational calculus, you'll often see that it's unavoidable to work with generalized surfaces, which instead of being embedded will have some singular points. Yeah. So in the setting that we consider, the natural generalization is to so-called stationary varifolds. Yeah. Which sort of loosely speaking, you can think of as some generalized minimal surface that has one embedded regular part and then some small singular part as well. Yeah. I'm putting this as a remark rather than as a definition, because in the setting that would ultimately interest us, namely in S3, these sort of concerns aren't in fact that important, because the singular set really only appears if the dimension is large enough. Okay, the last thing I want to say is that studying minimal surfaces is a very sort of leads to very sort of rich questions. Yeah, there's many examples. Even in a very symmetric setting such as S3, you get examples such as the equatorial spheres and the Clifford tori that we'll return to later. Yeah. Okay, so now that we have sort of this precise definition of what it means to be minimal, we can sort of return to the comparison between the Allen-Cahn equation and minimal surfaces to try to establish a more rigorous link. Okay, so to make our earlier observations about the phase transition region more rigorous, we're considering a sequence of parameters epsilon j that goes to 0 and a corresponding sequence of critical points, yeah, a sequence of solutions of the equation that additionally have a uniform bound on the energy. So this energy bound will have two consequences. Yeah. So notice, remember that the two weights are inversely proportional to one another. Yeah. So you see that as epsilon j goes to 0, the potential part becomes quite large. That is sort of unless u takes values close to plus or minus 1. Yeah. So this potential sort of forces you to go into these homogeneous regions. The kinetic term basically works like a penalization. Yeah? So instead of sort of randomly jumping between -1 and 1, it penalizes the transition and ensures that it happens in a more orderly fashion. Sort of okay. So this is the sort of the heuristic behind the convergence. Yeah. Rigorously can be stated as a theorem of Hutchinson and Tonegawa from the year 2000. Yeah? So what they show is that the nodal set converges to a minimal hypersurface, considered in sort of this generalized sense that we defined earlier. And also the energies converge to the area of this surface. Yeah? So there's two caveats here. Remember that when we looked at this splitting, there was this universal constant that we recognize again here. And the second caveat is that there's some integer that appears as well. Yeah, so you can the surface can appear not only once, but sort of multiple copies of itself. Yeah. So two remarks before I explain a little bit more about the significance of this this integer. So I'm going to change the two items that appear before the theorem. Yeah. So remember that there were sort of two things I wanted to say is that, first of all, everything interesting that's happening concentrates near the transition region. Yeah? But second, that the to sort of make the arithmetic geometric mean sharp, you wanted the two energies to be similar to one another. Yeah? So this is exactly what the second term sort of says, that the discrepancy between these two energies goes to 0, which again, on a heuristic level, maybe justifies why one might expect a convergence such as is expressed in this second term. Okay, so what is this integer n? I drew two pictures to illustrate this. On the left-hand side, you will recognize the description I gave at the beginning. Yeah, so this is sort of what you would consider typical behavior of uj. So you should think of this as, you know, we're taking a transverse section of the level sets, and there's sort of like an n-dimensional level set going into the slide, into the beamer. So on the right-hand side, I illustrated sort of pathological behavior where uj, instead of going straight from -1 to 1, goes from -1 to 1, and then back to -1, back to 1, and then back to -1. Yeah, so n in this sense sort of would represent the number of folds of the level sets. Yeah, number of times you switch between the two values. It's a little bit difficult to convey the importance of this number. Yeah, people working with minimal surfaces are sort of well aware of the difficulties that are associated to multiplicity, especially as it relates to regularity theory. Yeah, maybe sort of for the people who don't work in this field, I could just say that if, say, you were trying to establish a bijection between minimal surfaces and solutions of the Allen-Cahn equation, on the other hand, this is sort of this is a little bit bothersome because you'd have different solutions converging to what is ultimately geometrically the same surface. Yeah, so maybe in this sense, you can appreciate that it's a little bit bothersome. Yeah. Okay. So this marks sort of the end of the first part. Remember, here I wanted to sort of give an impression of the relationship between minimal surfaces and the Allen-Cahn equation. Yeah. Sure. Yeah. That's a good question. I think okay, so it depends. Yeah. So it depends. For example, try not to get this wrong. Yeah. But for example, one thing, if you're asking about the multiplicity one case, for example, yeah. So if you want to get it as the limit of a nice sequence of Allen-Cahns, then you notice that the fact that you cross from -1 to 1 means that you get an orientation on your minimal surface limit. Yeah. So if it's oriented, so really the right condition is if it's two-sided, yeah. And the kernel of the Jacobi operator, if that means something to you, if that is 0, then you can get it as a solution, a limit of Allen-Cahns. In fact, I think what is the sort of the right condition is that if you're integrable, yeah, if your kernel is integrable in the sense that it's generated by families of minimal surfaces, then you can get this as a limit. Does that make sense to you? So if I remember correctly, there's a result by two people from Chicago, ricerca and Pedro Gaspar, where they show that if the kernel is integrable and your minimal surface is two-sided, then you can get it as a limit of a multiplicity 1 Allen-Cahn. And as far as I know, this is sort of the proof is sort of a Lyapunov-Schmidt reduction, and it's based on earlier work of Bakar, where he showed the same thing, but if the kernel is 0. Yeah. Okay. So we've established the connection. Next, let's look at some variational properties. Yeah. Okay, so this is motivated by the problem of constructing minimal hypersurfaces. The setting that we're considering is we have an ambient manifold that's compact without boundary, and we want to construct minimal surfaces in this. So traditionally, this would have been done by the Amgon-Pitts min-max method, with sort of the drawback that the arguments really only are accessible to people working in geometric measure theory. Yeah. So the serious bottleneck to resulting to a different sort of argument was a lack of sort of regularity theory, sort of a sharp regularity theory for stable hypersurfaces. So this regularity theory was achieved in the years sort of 2014, I think, by Vikramasekera, who sort of sharpened earlier regularity theory of Shane and Simon. So what this allowed is that instead of working in this sort of a GMT setting, you could replace the construction and go instead via this Allen-Cahn equation. So this sort of has two steps. First, you use these variational min-max arguments to construct solutions for a given epsilon, and then you study the limit as j tends to infinity. Yeah, so and it's in the second step that the regularity theory becomes important. So these min-max methods were implemented by Marco Guaracco, first for one parameter, and then later with several parameters by him and Pedro Gaspar. One thing I can mention, so I said I want to motivate variational considerations by min-max constructions. And one natural way in which this is the case is that a solution that's constructed using p-parameter methods will automatically have most index at most p. Yeah, so Jada explained sort of a justification of this yesterday. Okay, so let's look at the most index a little bit more detail, given that it's so important for the talk. Yeah, so the most index of a solution U of the Allen-Cahn equation is defined in terms of perturbations defined on the manifold M. So what we do here is that we perturb U in the direction of phi and look at the variation of the energy at the quadratic order. Again, sort of from the same functional, you recognize one kinetic term and one potential term that now is differentiated twice. So up to integration by parts, this is basically just a standard linear elliptic operator. So we'll denote this L sub epsilon u and call this the Jacobi operator of our critical point. So as is standard for elliptic operators, it has a discrete spectrum that goes to infinity. Then sort of the definition of the Morse index and of the nullity becomes quite simple. Yeah? So the index of u is simply the number of negative eigenvalues, or equivalently, the number of sort of directions in which we can decrease the energy. Similarly, the nullity is just the dimension of the kernel of this operator. So, okay, so now next I want to define the index of a minimal surface. And just in terms of how the slide is structured, you can notice a similarity in the two concepts. Yeah? The difference is here, instead of perturbing sigma by an ambient perturbation, we do this by a function phi that's defined on the surface itself. And sort of another difference is that, you know, the operator looks a little bit more complicated, yeah. But fundamentally, it takes the same shape, yeah. So you have the Laplacian and then plus some zero order term. Let me explain a little bit what these terms mean here, yeah. So A sub sigma is the second fundamental form, so the curvature of your surface, yeah. We're perturbing in the direction of phi times n, so the unit normal to our surface. And there's a term that sort of involves the Ricci curvature of our ambient manifold. Yeah. Okay, but that sort of being defined, and the rest of the properties is sort of defined in the same way. The spectrum is again discrete and goes to infinity, and the index corresponds to the number of negative directions for the second variation. Same thing for the nullity. So one thing I wanted to say before I move on is that if you look at the sign of the zeroth order term, yeah, so there's this curvature squared plus this Ricci curvature term. You can tell that if the Ricci curvature is positive, then this whole sign here is positive, and you'll find that automatically the index has to be at least one. Yeah, so there's at least one negative perturbation. Yeah, maybe we'll keep this in mind for now. So three reasons why one might care about the index. Yeah. So first of all, it's a natural thing to consider from a variational point of view. Yeah. The second point I want to make is that it's useful as a sort of a geometric invariant, something you can use to distinguish between different surfaces. And the last thing I wanted to mention is that it's the fact that the curvature appears in the definition of this operator. It might seem cumbersome, but it actually turns out beneficial, right? Because it means that control over the index or the spectrum of this operator will give you some control over the curvature. Yeah, just a sort of a motivation for defining these things. Okay, so the consequence of this is that if instead of having only an energy bound, you additionally have a bound on the Morse index, you get improved conclusions on the minimal surfaces that appear as well. Yeah. So here's the sort of two complementary bounds that can be shown. The first one is an upper bound for the index of the surface. Yeah. So if, for example, uj was constructed by some p-parameter min-max, then the surface that would appear in the limit would have the same index bound, yeah? So would have index at most p as well. So this was first proved for orientable minimal surfaces, and later generalized by Pedro Gaspar to surfaces without any sort of orientability assumption. I should say that although I'm specializing to S3 on this slide, the theorem really holds regardless of which ambient manifold you're considering and which dimension you're considering. So this is not so for the second bound, yeah, that I'm citing here, where instead of bounding the index above, we're bounding it below, yeah. So here there's the index and the nullity that's being considered, so the negative and zero perturbations of sigma, and it's bounded below by the analogous quantity for uj. So notice that the bounds sort of go hand in hand. Yeah, maybe you don't have to remember specifically which one goes where, but maybe remember that. Keep in mind that we can control both sides of the index. I should also say that the reverse bound, this index lower bound, is a lot more difficult than the upper bound. Yeah, and it's sort of closely related to the proof of multiplicity 1 convergence, which showed that, in fact, if you have a bounded index, then these multiple folds that I was warning you about earlier can't happen in dimension 3. Yeah, so this is work by Otis Chodosh and Christos Pantelidis. Okay, so we've finished the first part about the connection between the Allen-Cahn equation and minimal surfaces. In the second part, we motivated the Morse index. We defined it for both the Allen-Cahn equation and minimal surfaces, and we looked at some consequences. Yeah. So now let's go to the third part, where we specialize to results that are valid in the 3-sphere. Okay, so in order to state these results, it's useful to know a little bit more about what the minimal surfaces in S3 actually are. Here I'm sort of listing the most simple examples, and to define them, it will be convenient to consider S3 as a subset of R2 cross R2 with an X variable, with sort of one variable for each factor. So using this, one first has the equatorial spheres that one gets by intersecting S3 with some hyperplane in R4. Yeah. These are the simplest examples. Next is the Clifford torus with genus 1, and that's obtained as the product of two circles with the same radius. Yeah. And sort of the third example, or the third example consists of a family of surfaces, of which there are infinitely many, namely these Lawson surfaces. I should say that when I say Clifford torus or equatorial sphere, there's just one of these surfaces, but really a whole family. Yeah, this is because if you act on the manifold on S3 by some isometry, if you rotate your surface, you get a copy of the minimal surface that is basically identical. Yeah, so index, genus, etc. don't change under this action. So there are several things that distinguish the equatorial, so the first two examples, from any remaining surfaces in S3. They're intimately related to the symmetries of the sphere. Yeah, so it can be stated in sort of two ways. First of all, if you look at the stabilizers of these surfaces, you'll notice that the orbits of the stabilizing groups are large surfaces. Yeah, so they're codimension codimension 1 surfaces in S3. Maybe if you look at the Clifford torus, for example, if you look at so it's stabilized by SO2 cross SO2. Yeah, so rotations of the two factors independently. And the orbits of this action will be tori, where the radius varies inversely between the two factors. Yeah, so as one factor increases, the other decreases. Yeah, but so you get a foliation of S3 by these tori. Yeah? So this is one sort of a significant property of this Clifford torus. Similarly, for the spheres, you will get a foliation by CMC spheres by varying the radius. So the second fact is related to the infinitesimal action of rotations. Yeah. So if you don't consider the whole kernel of the Giorgi operator, but only that which is generated by killing vector fields, you obtain the so-called killing nullity. Yeah. So this means that if you only look at vector fields which are generated by isometries, this is sort of the part of the kernel that you would get. So by definition, this will be smaller than the nullity. And sort of the useful part is that it behaves in a completely different way. Yeah. So because it can be described in terms of the group action, yeah, instead you will have here sort of an upper bound for the nullity instead of a lower bound. Yeah. So again, maybe it's not so helpful to remember. It's not that necessary to remember which way this bound goes, but maybe keep in mind that we have some helpful control over the killing nullity. Yeah, that's not available for the full nullity. So I mean, and why is this helpful for the spheres and the torus? Is that sort of having this control is particularly useful when instead of having an inequality between the killing nullity and the nullity, we actually have equality. Yeah, and this is the case for both for the sphere and for the Clifford torus. Yeah, so one says that they're integrable through rotations. Okay, so maybe let's think about these surfaces in terms of the Morse index. Yeah. So calculating the Morse index of the sphere or of the torus isn't that complicated. Yeah, it basically amounts to computation, and this shows that for the Clifford torus, this has index 5, and as I just mentioned, the nullity and killing nullity are the same, and the kernel is 4-dimensional. So what is more difficult to show is the converse of this result. Yeah. So what Urbano showed in the 90s was sort of he gave a characterization of minimal surfaces in terms of a low index. Yeah. So he showed that a minimal surface in S3 with index at most 5 would necessarily be either an equatorial sphere or a Clifford torus. Yeah, so one of the first two examples. So our aim is to give an analogous result, but for the Allen-Cahn equation instead. Instrumental for this will be the symmetries of the torus, yeah, which I mentioned earlier, sort of has this nice group action by SO2 cross SO2. Yeah. So if you exploit the properties of these symmetries variationally, you can show that at least for small enough epsilon, you will have a sort of canonical solution that is basically analogous to the Clifford torus. Yeah. So maybe say in which sense I mean this is that first of all it has the same symmetries, so it's SO2 cross SO2 symmetric, and second it vanishes exactly on this torus. Yeah. So the one thing. So basically the level sets of this solution will be these tori that I discussed earlier. Yeah. So parameterized by this angle theta that I described here. Okay. So I can state my first result. That's precisely what I just mentioned. Yeah. So provided you have some energy bound, then for small enough epsilon, the only solutions of the Allen-Cahn equation in S3 would be if you have index 5 this canonical solution, or with index 1, you'd get an analogous solution around the sphere. Yeah, but maybe let's concentrate on the Clifford torus. So I mentioned, so I give two caveats. Yeah, so you need to assume that the epsilon is small, because above that the solutions don't exist. And second, that is only true up to rotation. Yeah, so you need to precompose U by some isometry, some element of SO4, to actually get this canonical solution. Okay, so as a corollary of this, you get that the Allen-Cahn functional is more spot for low indices, or indeed, sort of, if you combine this with the results of the Wilmore conjecture, you also find that it's more spot at low energy levels. Yeah. So if you have basically the energy level of a Clifford torus plus some delta, then you're more spot in this range. Okay, before moving on, I should say that this isn't the first rigid. I mean, so I call this a rigidity result because it says that in this low index range, you're not flexible. Yeah, so you can only be this equal to this canonical solution. So that there was earlier work on rigidity by Guaraco, Marcus, and Nevis, where they were looking at surfaces that have a zero kernel, and a little bit later by Cajou, Gaspar, Guaraco, and Matthijssen, where they were looking at ground states of the energies, so an energy level a little bit lower. Yeah. So most, you know, so for most to be most functional, it means that your critical points are right. Does that? I mean, maybe I'll still answer for the rest of the room. Most spot functional basically means that your critical points will appear are not isolated, yeah, so not isolated, non-degenerate, but they appear as manifolds of critical points. Yeah. So in this case, this is sort of related to the group action. This is what your solution space will be. Okay. So notice that this is the first result I'm stating. The second result holds in a broader setting, and is instrumental in proving the first. Yeah. So here this holds regardless whether we're working on S3 or a manifold of higher dimension. The only assumption that we need to make is that the Ricci curvature is strictly positive. Yeah. So the result I'm considering here is describes the interaction between the nodal sets of two solutions. Yeah? So epsilon is fixed on this slide, and we look at two arbitrary solutions of the equation. These might have small or large energy, or small or large Morse index. Yeah, doesn't matter at all for this result. What it states is that if you have some topological hypotheses on the zero set, then necessarily they have to intersect. Yeah? So specifically, here I'm stating it in terms of the connectedness. There are sort of other similar characterizations in terms of you know, the orientation, etc. Yeah. So, but here I can say if the nodal sets are respectively connected, then they have to intersect. Yeah? They have to have some overlap. This is sort of, yeah. No, for any epsilon. Yeah. So I say that this is analogous to a classical theorem in minimal surface theory called the Frankel theorem. Yeah. And this is in precisely the same setting. Yeah. So we still have a manifold of any dimension and positive Ricci curvature. Then two minimal hypersurfaces necessarily have to intersect. Yeah. So it maybe seems like an innocent result, but it's quite fundamental to minimal surface theory, and was used, for example, by Marcus and Nevis when they proved the Yau conjecture and positive Ricci. Yeah, so this is a crucial step in this. And the second thing I wanted to make is that the analogy is not quite perfect because for minimal surfaces, there's no topological assumption. Yeah? So you don't need to assume that the surfaces are connected for this to be true. But in fact, it actually proves that surfaces have to be connected. Whereas as here, the result is false if you drop this assumption. Yeah, so there's some examples in the paper by Guaraco, Marquez, and Neves, where they show that they basically construct multiplicity 1 and multiplicity 2 solutions, where you cross either exactly at the equatorial sphere or above and below. Yeah. So in this example, you'll see that the nodal sets of this are disjoint, don't touch. So this topological assumption is necessary here. Okay, so I claimed that this was useful in proving and characterizing the low index solutions. So let's try to give a proof of the first result, assuming this fractal property. Maybe can I ask how much time there's left approximately? Plenty. 15. Oh, okay. Cool. Okay, so there's two steps involved in the proof. The first one, one establishes the symmetry of the solutions. So basically, this follows from the index bounds that I presented earlier. Remember that if the dimension is 3, then we don't have only index bounded above, but also below. Yeah, so on both sides. And this allows the simultaneous conclusions of these 3 points. Yeah. So the first one is the nodal set has to converge to some minimal surface, and this minimal surface has index at most 5. Yeah, so Urbano's theorem shows that it has to be either an equator or a Clifford torus, and because the index is bounded below, it has to have index 5 and actually be the Clifford torus rather than the sphere itself. Yeah. The second is by combining the index bounds with the way the killing nullity behaves. Yeah, you can show that these UJs have the same nullity and killing nullity as the limit that they have in the limit, as the Clifford torus. Yeah, so namely they're both 4. And finally, you can show that the stabilizers of UJ, so their symmetries, converge to the stabilizer of the torus, yeah, in some Hausdorff sense, for example. Using a Lie group theory, you can deduce that actually not only does it converge to this, but they have to be conjugate by some fixed element. Yeah, so this means that if you rotate UJ by some matrix in SO4, it will have exactly the same symmetries as SO2 cross SO2. Okay, so this is establishes the symmetries of UJ. Okay, so we have this as a first step, that we rotate UJ by the right element so that we get this SO2 symmetry. As a direct consequence, its level sets are all SO2 cross SO2 symmetric. And in particular, the nodal set must be an orbit of this SO2 cross SO2 action. Remember, the orbits of this action are really nice. Yeah, so there's this central Clifford torus where the 2 circles have the same radius, but then on the left-hand side you have one factor increasing, the other decreasing in radius, and on the right-hand side the inverse happening. But they're all disjoint tori. What this means is that there's only 2 possibilities. Either UJ is disjoint from this the central leaf, or else they must coincide. But now we can invoke the this Frankel property of the nodal sets. Yeah, so they can't be disjoint orbits because they have to intersect. Yeah, so in fact, not only do they have to intersect, but actually be coincide. Yeah. So then you can sort of apply a maximum principle to conclude that having the same nodal set means that you have to be the same solution. Yeah. So up to a change of sign, uj has to be equal to a canonical solution, and we have precisely the desired conclusion. Yeah. So for small enough epsilon, the only solution of the Allen-Cahn equation that there exists with index 5 has to be this canonical symmetric solution. And the same thing applies, although I'm not stating it here, the same thing applies to the equatorial spheres as well. Sure. Okay, so the first step is okay. I mean, so there's this theorem in when you study Lie groups that's called, I think, like the good neighborhood theorem. Must be a conjugate. Yeah. So there's this theorem that says that there's a neighborhood of SO2 cross SO2, or indeed, I think, sort of any compact Lie subgroup. That so that there's a distance so that if you're that close to this compact subgroup, you actually have to be conjugate to this. Yeah. Okay. So this proves the first result. I had prepared maybe okay. That's a good conclusion to what I want to say is that I've stated everything for S3, but in fact most of the arguments apply in a more general setting. Yeah. So for example, you can get a similar rigidity result in higher dimensional spheres if you replace the Clifford torus by sort of the right analogon. Namely, sort of instead of considering S1 cross S1, you now have SP cross SQ. But the important points about, having the nullity and killing nullity be the same, and having this nice group action, these are still preserved even in higher dimensions. Yeah. So some things are lost, like this Chodos-Mantolidis result that that gives you multiplicity 1 isn't valid anymore. So you sort of have to add this to the assumptions here. Yeah, in the sense that you have to assume that the energy is close to the area without this factor n, without this multiplicity. And you assume that the nodal set is close to these SP cross SQ. But given these two things, up to this necessary rotation and change of sign, there's only one sort of canonical solution with these hypotheses. Yeah, with sort of the same arguments apply with basically only minor modifications. Yeah. Okay. So maybe I'll finish here, and this seems like a good place to finish. Yeah. Thank you for your attention.
Thank you, Fritz, for your very nice talk. Are there questions also from online audience? If you have some questions, just turn on the mic and ask for it. I'd actually had one sort of curiosity during your talk. Is there some conjecture or some possibility of having something like a Yau conjecture for the Allen-Cahn equation? Or
so in positive Ricci, you want infinitely many?
Yeah. Or is it ruled out? It's stupid for some reasons.
So I think so one problem is that so when you're considering all these minimal surfaces, implicitly epsilon is 0. Exactly. Right.
Yeah. So I can see two kind of conjectures. The first one for small epsilon, and then one for any epsilon. This is why I asked you.
Yeah, but
about
right.
that depends on epsilon.
So I think when you have a positive epsilon, you can only have so many solutions. Yeah, that's my intuition that I'm answering with now. I think you can only have so many solutions, and as epsilon goes to 0, you get more and more complicated solutions.
Yeah.
So you'd presumably be able to capture all of these minimal surfaces, but only as epsilon goes to 0. Yeah, so say if you have some super complicated surface, then to capture this using Allen-Cahn, you need to have epsilon small enough depending on this surface. Yeah, so you can't choose this uniformly.
Okay.
So I think there's only finitely many, up to some rotations or whatever. But eventually you would capture them, I would assume. Yeah.
Many they become more and more.
Yeah, you get more and more solutions.
Okay, so this is your intuition about it.
That's how I would answer. Yeah.
Okay, but it's not still investigated, this question? Do you know something about it?
I haven't seen it, no.
I see. Okay, it's very interesting to me. Can you thank you, because it seems interesting.
Before you said that, as far as I understood, and maybe I'm completely wrong, if you take a minimal surface which has kernel equal to 0, which I guess it's equal to the nullity, but maybe it's something completely different, and then I stop here.
No. I mean, you're right.
Okay.
Except that you're assuming that the metric is bumpy as well, right? So
yes.
If the metric is bumpy, then sure, yeah.
Awesome. Okay. That's what.
So bumpy in the sense that the kernel is 0, which is true for some generic set of metrics in a bare category sense. Yeah.
Okay. Are there some other questions, Alessandra?
I already know before asking, but my question is extremely vague. Does something of your work works also in the case of the evolutive Allen-Cahn? Have you ever tried to study the problem?
Well, so the funny thing is that the last slides that I skipped over, they were so one funny thing is that this thing about these nodal sets intersecting. Yeah, so it looks like a completely static result, but it turns out that you prove it via a sort of a dynamic argument using the parabolic Allen-Cahn equation. Yeah, basically you sort of imitate. You do a this the mean curvature flow with positive mean curvature. You basically emulate sort of these same sort of properties and get the conclusion from this. So the parabolic Allen-Cahn equation has a place in this work via this argument. Does this answer your question, or
yes,
which?
Yes.
Okay.
There's another question by Federico.
Just one thing. You said that when epsilon is fixed, let's say epsilon is 1, you expect finitely many solutions. Is this like proven? Is this an intuition? Something else?
It's sort of, it probably, I mean, I'd have to check about okay, maybe I should say, I'm not sure exactly what I'm claiming. Yeah. I think some version of this is true, but not precisely the version that I quoted and that you sort of are asking me about. For example, because if you look at the sphere, once you get the canonical solution, you can rotate it as well, right? So then you get infinitely many for sort of trivial reasons.
Are there some other questions? If not, we thank once again Fritz. And let me close with some concluding remarks. We thank you all very, very much. Let me thank, first of all, the speakers who really were able to get what what Alessandra and me asked from them with these very beautiful talks that we hope inspired you as much as they inspired me. They were very, very interesting, and they were able really to get what Alessandra and me desired. So thank you very much. Thanks to all the participants for having enriched these 2 days. We hope you appreciated the mathematics and also that you had some good time, like us, like me. And then let me thank the technicians that were able to allowed for this workshop to be given in a blended way. That's something that's still a little difficult to to realize in a proper way, but I think it's that everything went in the best way it could. And finally, let me thank the real organizers of the workshop that luckily are not here. That's the Giorgi staff that really did a very wonderful work and substantially left me and Alessandra just dealing with the scientific part of the workshop, and this was incredible for me. It's been a pleasure organizing these things, and so thank you again, and we go having lunch together now for those of you who are interested. And I recall for those of you that want some more geometric analysis, the seminar by Luca Benatti at the University of Pisa at 15 p.m. or something later. So after lunch, there's this new seminar. So thank you all, and I clap your hands for you.